All right, let's get started for today. So this is Tuesday, but we have a short week this week because of Easter break, right? So there's no class on Thursday or Friday or Monday, but that only affects us for Thursday here. Um, but to adjust for that, we will work through the class exercise today. And talk about quantum computer. And then there's this activity where you can learn more about quantum computer. I'm going to add one more option, another video for you to watch here. So you can watch, do one of those. And then we're also working on the project. And the next part of the project is kind of do a minimum kind of viable option, trying to get kind of things set up. I had this due for this next Sunday, but with Easter break, I decided to push it off there until so we have more time in class to work on this. So next week we'll have some time in class to work on this stuff. So by the 27th, so not this Sunday, but the Sunday after that, we want to try to have not your whole project done, but some minimal, some basic part of it working there. So something, set up some software installed, maybe a camera working or something like that on your project. And then we can add to it there. I did bring our devices here. I mean, our Pis and stuff in case any of you want to grab one over Easter. Sometimes people have downtime over the next week, and so if you want to grab your Pi and bring it home or something like that, we won't be using the Pis for anything other than the final project from now on. So one thing you will see is that often with the final projects, you may have to reformat your SD card. So like, let's say you're doing RetroPie or as an example, or like a security system, a lot of those have images that are pre-built in a whole operating system installed. So you take your SD card out, you bring it onto a Windows PC and you re-image it with a new image, a new operating system, and then you stick that back in your Raspberry Pi and boot up. So it has a lot of the software pre-installed there. So just know that you can do that now. We're not going to be using our Raspberry Pis for anything else there. Some people do like to have an extra SD card, and sometimes people just have extra SD cards around. I know for my little cameras around, I have quite a few little SD cards sitting around. And you only need like a 6 gigabyte, 8 or 6 gigabyte SD card to do that. So if you want to just do it on another SD card, that's fine. Also here. Some of you need some devices. So there are a number of people doing like weather stations where you're going to need some sort of sensors, like a temperature sensor or maybe humidity sensors. So we have some of those available. Some of them are looking at like security cameras or pet cameras, and you'll need cameras. So we have those. Again, you don't have to grab them now, but I just wanted to bring this stuff down in case. And same with like the joysticks and stuff like that, in case you're doing a gaming thing. If you want to play with this or try this stuff out over the break, that's just fine. I know some people, it gets very hectic during these last weeks, and where Easter is very close to the end of the semester, you probably have final papers or projects or exams in almost every one of your classes, and you're trying to balance that off. So again, some people like to take a class like this and try to get ahead of the curve over Easter. So if you want to do that, you can. I certainly don't expect you to do it, but I didn't want to prevent you from doing that either for that. Just for your information, there's a couple things that no one is doing. And so we have, in case anyone's interested, we still have this car that you can drive that has a Pi built in, and then we have these servos and stuff on this arm that no one has. And same with this touchscreen. If you need that for something, those are some devices we still have. No one is using at all for a project. So if you're interested in working with any of those are all still available. Oops. Okay. Questions on the final project? So what are we going to do today? we're going to go and talk about quantum computing. That's actually covered in our textbook. It is, in some ways, people think it's a very new topic, but it's actually been around for quite a long time. People have been working on it, talking about it, trying to figure it out for quite a long time. So it's in a chapter of our textbook, because again, back at that time, people thought we were right around the corner from a break in quantum computing here. And so it talks a little bit about quantum computing. One of the things that talks about is Moore's law. And what is Moore's law? So assume most of you have heard of Moore's law before. So let's just review it. So Moore's law is named after Gordon Moore, who was in Intel in the 1960s. And kind of noticed that every 2 years or so, the number of transistors they could pack onto a chip was doubling, and predicted that that would continue there forward. Forecast doubling every 2 years for this. And this has been amazingly true going forward, that the number of transistors on a chip has largely doubled every 2 years. And we have this curve. Now, this curve, one thing to notice is this is a log curve. So this shows a straight line, but this is actually exponential growth, because you notice we start with 1,000, 10,000, 100,000, 1,000,000, 10 million, 100 million. So every time we step up, it's 10 times bigger than the previous one. So that's makes it a log graph for this. So we see this kind of linear, or this growth of doubling every few years for that. And what happens is that not only do the number of transistors then double on a chip, it also generally means the speed, heat, size, all that stuff doubles often, because again, we're packing everything in closer, making things smaller. Things can be a lot faster and things like that. But a lot of people are saying that we're reaching kind of the era where we might not be able to continue Moore's law, because we're kind of getting down to almost the atomic scale of things, where nowadays our transistors and stuff like that, our components we're packing onto our silicon wafers are so small that we're running into issues where they're just, they're just a few atoms across, and we're running into this atomic barrier here. Again, there's lots of people looking at ways to change that and improve it there. But again, there's other people, there's a good argument that could be made that we won't see this doubling, certainly maybe for the next 20 years, like we have for the last 20 years in some ways. Again, they're also talking about, they talk about a third dimension here. Right now, we're working with flat silicon chips, and another idea would be to, rather than put everything on one chip, to put it on multiple layers of silicon. This is actually done with our circuits. When we do our circuit boards, we actually have on our printed circuit boards, the bigger circuit boards, multiple layers. I have a friend who designed circuit boards, and he's young and hasn't done this very long, but he designs on boards that are like a dozen layers deep, and so he can run a wire up and over and stuff. It's like wiring a 12-floor building. You can go up, over, down, and stuff like that. But again, that's not on silicone and not as fast as that, but people are experimenting with doing the same thing with silicone in different ways, not so that our silicon wafers will not just be flat wafers here. And then we talk about some of this disruptive technologies, and one of them is quantum computing here. We're not going to get into quantum physics very much, but quantum physics is a very complicated area or way of looking at the world. as opposed to classical mechanics, we would say, in that we see matter having not like we don't see an atom with protons and neutrons moving around it. We don't see those elemental particles in quantum physics. We see kind of waves. We think of everything kind of as a wave, more like a probability wave of where it's at there. So, you know, like an electron is not a particle circling around an atom. It's a cloud of probability of where the electrical charge is around an atom. And same with everything. Everything is this sort of so, you know, electron is never at one spot. It's always at multiple spots at the same time with different probabilities. There's a whole math to describe this stuff. And yeah, and there's this Heisenberg uncertainty principle where that if you try to nail down where like an electron is specifically, you can't very well. You know, looking at it changes the characteristic of it in some ways. So again, I'm not an expert on quantum physics. Now, from this, physicists started proposing, well, to understand this weird quantum world, we might want to simulate it with a quantum computer somehow, and try to simulate this state of quantum fluctuation in our computing devices. And so that since the 60s, they've been theorizing what a quantum computer could look like and do there. And again, we talk about this spin, that these objects will have a spin number, and they'll be spinning around some spin value. And again, we can't necessarily nail down what that spin value is. And so there's they've been developing this quantum computer. And the main thing with quantum computers, where in normal computer, we have these bits that are either on and off. In quantum computer, we have these qubits or quantum bits, and they're not 0 or 1, they're kind of both there. They can take on either value here. And only when we try to read them do they then take on some exact value. And there's also something called quantum superposition, which says we can tie multiple qubits together into a longer quantum state to store not just one bit, but more complicated data in these things. So, I mean, I was saying quantum superposition. That superposition is the fact that they can be 0 or 1 at the same time. Quantum entanglement is what we use to entangle them so that they act as one big, larger unit for that. So, I'm going to look at some articles. Again, it's hard to figure out where to go. Almost every big company out there is researching quantum computers at some point. So I'm just going to look at IBM and a little bit of what IBM says about this as just one example of this, I think. And again, IBM is trying to sell consulting resources, expertise. So again, part of this is part sales, that they know what they're talking about related to this stuff. So again, they talk about 4 key principles. Superposition states that a quantum particle can be not just one possibility, but the combination of multiple possibilities can be 0 and 1 at the same time. Entanglement is that we can have multiple quantum particles correlated or tied together here. We run into some problems with interference in different ways and how to read this. They talk about these qubits here, what a qubit is for this. often, and there's different ways to try to represent qubits. So these are some examples of how different companies are trying to represent a qubit in different ways. A lot of these ways involve superconductive materials. And currently, in order to make anything superconductive, we have to make it very, very cold, like absolute zero, close to absolute zero kind of cold. Liquid hydrogen kind of levels of cold for this. So this talks about it, and again, talks about it, compares it to classical computing here. But really doesn't get, talks about how it could be superior to computing. So complex problems with lots of variables that interact in complicated ways can be modeled with these devices, with quantum computing. Like sorting through a huge database of molecules, stuff like that. Calculating very complex numeric calculations maybe might be something we could use that. But again, largely saying we can do it. Quantum computers scaled to simulate molecular devices could massively speed up and develop life-saving new drugs and treatments. Quantum computing could help enable petrochemical alternatives, find ways to combat the energy crisis. In machine learning, we could train models very quickly for this. So, and again, there's a whole course in quantum computing at IBM that you can go through for this. This is another article that just talks about quantum computing and has a little more detail of how this shows and some of the different states they want, and trying to show how this works and a little bit about how complicated this is here. So now while I'm doing this, let's have you start working on the exercise if you haven't already. So why don't you go back here, find the exercise, bring it up, and let's start looking at what's in that. So first one is Moore's Law. So is Moore's Law dead? I want you to find an article published in the last 3 years that describes the future of Moore's Law here. So post the link to the article and whether or not it thinks that Moore's Law is dead. You can certainly Google Moore's Law dead, but again, if you just Google recent articles about Moore's Law, they should all talk about some of the limitations or the end or something like that for that. We talked about this third dimension. We commonly use multiple layers on printed circuit boards. So like your Raspberry Pi has 6 layers, but silicon wafers don't. We generally only have 1 layer on silicon wafers here for this. Let me just make sure. And so you'll find an article on multi-layered or 3D integrated circuits. So just so we're clear, so this is a printed circuit board. It's one of these, let me see if I can get this article here. It's one of these green boards you generally see around here. And it will have chips and other devices on it. So it'll have silicon chips on it for different things. But it itself is not one big piece of silicon. It is printed circuit board. And again, there are multiple layers on these circuit boards, and we run wires. So we will see some layers on the surface, the top layer or the bottom layer, but there are multiple layers in between. So that's not what we want. We want to look at silicon articles about where the silicon wafers are multi-layer here. So and the silicon wafer is what we see in, inside its chip. So these are silicon wafers. They're all shiny stuff, and then we use them to make devices. We print circuits right on there, and then we break them up and stick them on printed circuit boards and stuff like that for that. So they tend to be shiny. They're not screens. Some people look at those like, oh, those are the tiny display screens. Those aren't. They just are shiny because they're polished from this. So yeah, find that. See if you can find multi-layered integrated circuits or 3D integrated circuits for this. And then we can start to talk. We've been talking about quantum computing. And so we want you to define these terms in quantum computing for this. Now, on some of these things, I want actual articles. And some of these where I want the descriptions, you're free to use some AI to help you with that. Find descriptions of this stuff. So now I'm going to talk about some videos and talk about some applications and some strengths and weaknesses of this sort of example. I'm going to go back to these readings here. So there's a lot of news and hype out there that's saying that quantum computing is going to change the world and make, computers 1,000 times faster and everything like that. And so one thing I want to try to get through is hype versus reality with these and see if, I'm a little pessimistic of quantum computing, and maybe it's just because I've been around for so long and they've been promising stuff for so long and I guess I see significant issues with this sort of stuff. But again, I'm certainly not an expert in this area, but I want you to see some. You can certainly find lots of videos and social media talking and hyping up this. So I wanted to point out a couple resources that talk about kind of the opposite of this stuff. And then we're going to look at one example of this is the new discovery promoted by Microsoft in the last few months. But first I'm going to go to this article or this video that talks about quantum computer hype or not, or reality stuff. So anniversary.
If you have lots of readings to do, not just for your.
I'm going to go, I didn't put that at the beginning.
Okay. Try to use ordinary language, which of course it evolved to describe the things that we do encounter in the everyday world. You find descriptions of quantum mechanics that involve statements like an object can be simultaneously here and there and everywhere. And you find statements that jump off from that when you apply these ideas to quantum computers. You hear things like quantum computation creates every possible computation simultaneously. And you find things like quantum computation will result in an exponential increase in computing power, laying all of practical computation to waste. And you find statements like all of this is right around the corner. Now, the fact is, there is some truth to all of these statements, but if you take them at face value without digging a little deeper, it can be quite misleading. And that's why I am thrilled today to have conversation with my friend and colleague, Seth Lloyd, an expert in quantum computation, to help us sort this all out. So Seth Lloyd is a world-renowned professor of quantum mechanical engineering at MIT, and is currently working with a variety of groups to construct and operate quantum computers and quantum communication systems.
Hi, Brian.
Yes.
So again, when I'm trying to figure this out, I'm trying to figure out, what are some good sources of information out there. And so I found this source. I like this for a couple reasons. One is this, the main moderator here is Brian Greene, which is a well-known physicist with a scientific background. So I like that. I know who he is. I trust him. There. And again, he's interviewing, but and he's not an expert on quantum computing, although he knows a lot about physics. But he's then interviewing someone, an MIT professor who is working in this quantum computing stuff. So I like that. So I think this is a good place, to look for some of this information and see there. So they go on, they actually spend a lot of time talking about superposition in this two-slit experiment, basically showing that light behaves as a wave and not as particles. Photons are often can be seen not as particles as waves. So they're both physicists. They really like that stuff. And then they go on talking about some of this. I'm going to jump to specific locations. Now, one of the challenges with quantum computing is, again, like you said, one of the neat things is that it can solve all the problems at once. It reminds me of, we used to talk about making analog devices to solve problems. A common problem we have, that's kind of fun to play with is you draw a maze out and then there's one path from the start at the top to the end of the maze at the bottom. And can you program a little robot or a computer to go down all the paths and find the path that goes from the start all the way down to the bottom of this? And you can certainly program a computer, and there's different algorithms to try out different paths. When you get down the end, back up to the last turn and then take the next turn and keep track of where there's turns you haven't tried. It's a fun algorithm to do. But you can also think of this, you could create a physical device, an analog computer to do this. You could just build an actual little maze out of wood, and you could just pour water or plastic or pour water in the top, and water will flow down, try out all the paths. And if there's a path that gets to the end, the water will flow out and come out of the path. So you'll pour water at the top and you'll see water coming out of the bottom. And say, oh, yeah, there's a path. Now, it may not be very clear to you. How do you figure out what path? Because the water tries out all the possible paths, all the paths are getting wet. So what is the right path? So just because you can pour water in the top and it comes out the bottom, there's a path, but you don't know what path it is. And that's kind of what we run into a lot with quantum computing, is this extracting this correct answer here.
States that we hear kicked around a lot, that quantum computers will increase all calculations by this enormous exponential factor. But I want to, in our remaining time, dig down on that a little bit more, because as as I've learned from your community as well, that can be a misleading statement, right? Because if you're trying to undertake a particular task, and you are following every possible computation that might lead you to the answer you're looking at, well, how do you pick out the one answer from the many that all these many parallel computations would yield?
Yeah, I mean, that's great. And indeed, actually, when David Deutsch first proposed using quantum computers to do what's called a quantum parallelism.
Yeah.
buzzword that goes along with. It seemed, hey, we could solve really hard problems, we could search for all possible solutions for the way to like, get rich using cryptocurrency. Actually, people do use quantum convert computers to search for Bitcoin. But the problem with that is what we were talking about before, is at a certain point, you leave the quantum computer alone, you let these qubits do what they want. You don't want to look at them because when you measure them, they have to declare MI0 or MI1.
You lose your power.
You lose their power, that's right. In fact, it's considered very rude to look at somebody else's quantum computer in the laboratory operating because, if you sneeze, the quantum computer gets cold. So, all you can do is just you set all these quantum computations in parallel, quantum parallel. And then you just make a measurement and say, hey, what's the answer? You'll just get some answer literally random. That's not very useful.
And so the goal is presumably to make use of this weird kind of probability that's inherent in quantum mechanics, where, as we said before, it's not just positive. You can have these interesting interference effects that, if you were really clever, you'd be able to take the various waves and their various probabilities and somehow combine them so that the combined wave doesn't have all possibilities at random, but rather getting closer and closer and closer to some unique answer. And if you are clever in building your quantum algorithm, that unique answer that we see being built up from all these quantum waves will be the answer that you're looking for, even though you did not know what the answer was. That sounds incredibly difficult.
That was beautifully said. And when you said, I said, no, that can't possibly be true. Yeah, it's you have to remember, just even in the two-slit experiment, the interference is actually very important in the two-slit.
So they're talking about this interference, and again, this idea of you can see all the possibility, how do you measure that possibility? And so it is a problem, but again, there are ways around this problem. They have solved this in a number of ways here. So they talk about that. And then this person goes on and talks about some of the algorithms and applications to this. Let's see if I can pull up that section here.
Yeah, that's a great question. Of course, nobody knows the answer. We're all looking for new algorithms all the time. In 2008, my colleagues, Aaron Powell out at Austin and I realized that you could take this kind of like the mathematics of describing waves and solutions to wave equations is called vector algebra. And it's like you have these big arrays of numbers called vectors. You have big square arrays of numbers called matrices, and you can multiply the rules for multiplying them. And the Schrödinger equation and Heisenberg equation are phrased in terms of these laws of algebra. And we realized that you could actually use quantum computers because of this connection between the physical waves that are out there, these quantum mechanical waves, and mathematics. You could use it to solve all these problems involving linear algebra. And this actually then becomes potentially very useful because, at 2008, we didn't really have like deep learning and stuff like that, machine learning, let alone like scary but somewhat stupid like large language models. And so, but all the mathematics that goes, or the great majority of the mathematics that goes into this processing information for machine learning and AI is actually phrased in terms of these linear algebraic problems. So now we actually have a whole host of possible applications.
So again, one of the questions often is where can you apply, if we get a quantum or get quantum computers, what kind of problems can it solve? And it's good at like finding prime numbers there and breaking cryptographic stuff. It's good for like complex searching. But again, one of this new ways is that it's good maybe at more these vector arithmetic, vector calculations, and that's the heart of AI and large language models training. We do a lot of vector, computation here, and so possibly could help with some of that here. But the question often comes up is when, and I've been hearing this for a long time,
the intuition more than anything else. If you were to say, a time scale for realizing the full potential of quantum computers, do you put that 5 years, 2 years, 100 years, or is it just too hard to say at this point?
Well, my prediction, I try not to make technological predictions because you all, if they're on camera, because you always look dumb, like you did down one, but like, I think, people are working very hard, lots of like, well-known companies, our governments are working very hard to do this because of the obvious benefits of doing this. It's tougher to hope, I mean, very uncertain, I say 10 years plus or minus never. Well, okay, 10 years minus 5 plus never. Yeah.
So you do hold the possibility that we may never actually realize in the manner that, at least theoretically, we can imagine.
Well, so to be fair to quantum computing and quantum information and quantum information processing is a much more broader field than just building a quantum computer. So you can like play quantum video games. But because actually, if you look at problems like sensing and imaging and precision measurement, and then you're taking these quantum states by probing the world of like going on it, the quantum states come out, we process it. Quantum information processing allows much more precise ways of doing this. Already, Dave Wyman's optical frequency quantum clock, for which he got the Nobel Prize, is called quantum logic quantum clock, atomic clock, because
Okay, so again, they're saying, this is an expert in the field saying, 10 years plus or minus never, because again, there's still roadblocks we're not sure we're going to be able to overcome. Certainly we can do basic things with quantum computing now. The question is that how well will this scale up here? So again, I think you can find lots of videos that talk about the promise of quantum computing. I just want to play a couple that have the opposite view. And then we'll look at one that promises of Microsoft's new promise and amazing discovery if it turns out to be true. But here I want to point out this other one. This is a group.
If everybody has the same ideas and the same theories and builds in the same place, you're missing out.
So this is a group mainly talking from a financial point of view about quantum computing, and some of the what they're seeing is more of a hoax that all these companies, we're not going, they're just trying to raise money and get that, and they don't. This group of people do not believe that quantum computing is going to change the world for that, and that's their argument. So I just want to put that out there as alternative. There. Now let's look at Microsoft. And so we'll watch more of this. This is Microsoft's announcement that was just made earlier this year.
They model the laws of nature. That's the promise of quantum computing, but there have always been limitations. Now is one of our longest running research projects. Our team at Microsoft has been able to take a subatomic particle that has only been theorized until now, and not only observe it, but control it, creating an entirely new material and a new architecture for quantum computing. One that can scale to millions of qubits on a single chip.
This is not a work of science, it's a work of science and art.
I gotta be honest, some of these ideas are little science fiction sounding.
It will solve problems unsolvable by the combined power of all the world's compute today, and promises to revolutionize fields such as medicine, material science, and our understanding of the natural world. Our first quantum processor based on this architecture is the Majorana 1. Been fascinated with puzzles and challenges and a mixture of mathematics and computers. And so when I learned that there was this type of computer that didn't exist yet, but could solve problems that we can solve with our digital, all of the computers we had, I was just fascinated. I wanted to learn, well, how can I help that computer be built?
Over the years, I ran into problems that could not solve on the most powerful computers. But then over time, I realized, hey, I could solve that if I had a computer. A laptop can solve a problem of 10 electrons. A supercomputer can solve a problem of 20 electrons. But no classical computer in the world can exactly solve the behavior of 30 or 40 or 50 electrons.
The number 30, 40, 50 electrons, those numbers are seemingly small, but require up to lifetime in the universe timescales to solve with all of the world's computers operating together. That's until you have a scaled quantum computer that can solve these problems efficiently.
These calculations are so complicated that then if the classical computer was as big as that planet, it would still not be able to compute. Just to give you a concept of scale. And a quantum computer can do it, and can do it very, very well.
At the core of a quantum computer are these qubits. Qubits are like our classical bits, right? These are essentially zeros and ones in a transistor. And we need the analog of that in quantum computing. The analog is a qubit, a quantum bit that serves as that core information unit. It's where we store the information and then we process on those qubits to create computation and ultimately, get solutions back out. Now, there's many different ways, right, to create a qubit. The reason quantum computing has been so slow to progress is that the industry has been struggling with problems making qubits reliable and resistant to noise. Progress has been incremental.
The challenge is qubits are actually pretty delicate in general, so you need underlying qubits that are really stable. But you don't want them to come at a cost because you don't want your underlying qubits to be really big. That's one way to make them more stable, become really big. If they're really big and you're still going to need many of them, then how are you going to fit them all into your system? You don't want to deal with something the size of a warehouse. Then the second thing is you don't want the qubits to be slow, right? Because if the price you pay for getting something stable is you have to go really slowly, then the computation it might take you a month, ends up taking you a decade, and then it's not useful. People in the early days of computation used vacuum tubes, and then that technology actually could build very good computers with it. And then the transistor was invented, and the early transistors weren't necessarily that great, but it became clear over time as the transistor developed and the integrated circuit developed that this was going to be the technology of the future. In that spirit, that the first generation of qubits may not be what gets us to the next stage where we can really solve the kind of problems I was mentioning that are really important. And so we might need to invent a material, and therefore a quantum processing unit that has the right properties. So for us, we want something that has some built-in level of error protection. And a lot of those ideas actually were explored in the context of software, quantum error correcting codes, but you can actually build a lot of those ideas into hardware.
So the way you design that qubit matters. We see the states of matter every day. Solids keep their shape.
So just so you remember that in the exercise, your last thing is to talk about this chip that they're doing that we're working on now. So I want you to ask AI about it, which AI you want to ask, and ask it, provide a summary, find an article about it, and then your opinions or reflections on this here. So, okay, let me go back to this.
Liquids vary but keep their volume. Gases expand to fill the space they're in. All defined ultimately by how their atoms behave. But what if there were more? What if, under the right conditions, you could engineer more? States that have only ever been theorized, that would change how subatomic particles actually behave. 100 years ago, mathematicians predicted one such new state of matter, the topological state. And since then, researchers have been looking for a very specific, very useful quasi-particle within it, the Majorana particle. Last year, we were able to observe it for the first time. And this year, we're able to control it and use its unique properties to build a tahoconductor, a new type of semiconductor that operates also as a superconductor. With this material, we can build a whole new foundational architecture for our quantum computers, a topological core, allowing us to scale to not tens or hundreds of qubits on a chip, but millions, all in the palm of your hand.
Majorana's theory showed that mathematically it's possible to have a particle that is its own antiparticle. So it means you can take two of these particles and you bring them together, and they could annihilate and there's nothing left. Or you could take two particles and you bring them together and you just have two particles. Sometimes it's nothing, the zero state, and sometimes it's the electron, the one state.
So it really has taken quite some thinking, right? Some time to design a device, design a chip that can enable measurement of this literally elusive particle. We've designed a chip that is able to measure the presence of Majorana. Majorana allows us to create a topological qubit. A topological qubit is reliable, small, and controllable. This solves the noise problem that creates errors in qubits. Now that we have these topological qubits, we're able to build an entirely new quantum architecture, the topological core, which can scale to 1 million topological qubits on a tiny chip.
Every single atom in this chip is placed purposefully. It is constructed from ground up. It is entirely a new state of matter. Think of us as building the picture by painting it atom by atom. In a regular chip, the computation is done using electrons. We don't use electrons for compute. We use Majoranas for computing. It's a tiny new particle. It's half an electron.
When we look at the design of this chip, right, first of all, you can fit so much on just a small form factor, right? This chip can store over 1 million qubits, right? Over 1 million can fit on just this small form factor. In addition, we don't want to wait centuries or millennia for a solution. And so this chip also offers the right speed to get solutions from the chip in a reasonable, efficient amount of time. That's the beauty in this qubit design, the topological qubit. It has the right size, the right speed, and the right type of controllability. And all of that together means that it has an ability to scale like no other.
The way the system that we are constructing works is you have the quantum accelerator, you have a classical machine that works with it and controls it, and then you have the application that essentially goes between classical and quantum, depending on which problem it's trying to solve. Once the computations are done, the results are resynthesized from the classical side and produced back to the user as one complete answer. Where the quantum machine shines, it is able to do simulations, particularly in chemistry and materials, that are extremely accurate, as accurate as an actual wet lab experiment. Imagine a world where a scientist computes the material that they want, and they compute it to the accuracy that it's first time right. So when you walk into a lab, you don't need to experiment anymore. Imagine a battery.
Okay, I'm going to leave that there. So that was one of Microsoft's announcements. Let's see when that was a month ago, and it has 4 million views here. And at the same time, they released an article in Nature magazine, which is a top scientific journal, peer-reviewed journal describing this. So it's a pretty amazing announcement there. And you're thinking, Tom, are you still skeptical? It's Microsoft. It's a huge company. It was published in a well-respected scientific journal that's peer-reviewed, and they have this really nice video. So why am I skeptical? I deleted this. So there was, oh no, here. So 2 years ago, when I was teaching this class. We had the same sort of thing happen. We had a different great discovery in quantum computing that was going to change the world, this new type of quantum computing by this new startup there. And there was a video and all this stuff about it. But again, turned out not to be useful. There are issues in the final use of it here. So you look a little deeper at Microsoft, and those people are now beginning to raise some questions about Microsoft's discovery and what it actually means. There, reports have come out that although it was published in Nature, which is a peer-reviewed journal, like 4 of the 5 peer reviews said that it should not be published, and the editor overrode the peer reviewers on that stuff. I don't know if that's true or not, but I've seen that report there. We just don't have that much information. And again, the main question from people, reviewers, was that Microsoft's just not providing enough information to verify that this is true. And one of the problems we have with this sort of stuff is that if you're going to make a big discovery, change, create a new state of matter, change the way we understand physics, we need an amount of proof kind of equal to or more than the level of this discovery. So this is a huge discovery, huge change in the way we see things. And so we really need extraordinary proof for this. And people are not quite seeing that here. So in the same way, there are great videos that you can see online that talk about how amazing this is going to change the world. I just wanted to point you to one that says, maybe this isn't going to change the world as much.
Microsoft's big breakthrough in quantum computing. They announced that they achieved the first step for a scalable platform that could bring us to 1 million qubits quickly by using Majorana roots, a type of topological qubits. Other scientists have now had a closer look at the publicly available evidence, and that isn't looking good. I have a quick summary. If you want to build a useful quantum computer, you need qubits, or bits with quantum properties. There are many different ways to physically create these, and Microsoft has settled on a particularly difficult yet promising way called topological qubits. These have properties that are protected by conservation laws, and the states then remain coherent for a longer duration. That is, topological states keep their quantum properties better. This means that topological qubits could make it much easier to build large quantum computers, and that's the reason why Microsoft has claimed they can build a useful quantum computer in years, not decades. It sounds like a good idea in theory. In practice, it's proved very hard to produce even a single topological qubit. The biggest criticism that Microsoft faced after that press release is that they supposedly said they had a topological qubit when really the paper that they published explicitly said they did not. However, if you read the Microsoft press release very carefully, you'll notice it doesn't say they have a topological qubit. They weaseled around the question by talking of a topological core architecture.
So again, this goes over some of this stuff. And so again, it's still not clear what this is. So this could certainly be a life-changing event if this quantum computer and if Microsoft is able to generate something with 1 million qubits in the next 5 years. That would be amazing discovery. But again, it's still unclear. And again, I'm skeptical about this sort of stuff. I really wish it would be true, but I guess I've been disappointed there. I grew up watching sports, and I was a Minnesota Vikings fan back in the 80s, and they kept going to the Super Bowl and always losing the Super Bowl. So by the time I got to high school, I could not watch football anymore, and it was just so depressing to me. And now watching most sports is just very depressing to me. brings up childhood trauma of watching the Vikings lose. Okay, maybe that's not real childhood drama. I did not have a very eventful childhood. If that was my childhood drama, I'm sorry. But the same thing here is over time, I've seen, these sorts of great advances put forward again and again, and I've been disappointed. So part of me is just kind of preparing myself to be disappointed again. I wish it would. So anyway, it'll be interesting to see this, all relatively new. So I'm interested to see your point of view. I'm not very good at predicting the future or understanding technology. You think I would be, but when I saw the first, probably don't remember, but at some point there wasn't the World Wide Web, there wasn't web browsers, there wasn't HTTP. When I saw the web for the first time, I said, "Ooh, that's not going to work." There and said, when I saw when the first iPhone, I said, "Oh, that's not going to work either." So again, I'm not really good at a lot of these prediction sort of stuff. So I'll just warn you. But my point of view is I wanted to give you a mixed bag here, that there is a lot of hype and there's questions about reality here. And I think it's easy to find the hype. I mean, it's really fun. I like going on social media, go on any of your social media and just, search for quantum computer and you see the hype there. And so I just wanted to balance that with some of the negative, I guess, hype on the same thing. So, last thing we want to talk about is, well, if it's not if quantum computer might be changing, but if it's not, what other options are there out there? And so, some other things to look at, which I think we mentioned at various times. People have been researching carbon nanotubes, neuromorphic computing, memristors. So again, chips that are based more on a closer proximity to how the brain works. Right now, we emulate, a machine learning uses something called neural networks, which is a mathematical approximation of how a simple model of how neurons might work there. But these actually try to build them more out of silicone in different ways. We use electricity. There's always been looking at using optical computing there. We do use fiber optics to transmit data long distances, but we don't use it inside our chips there. We use this von Neumann architecture. There's non-von Neumann architectures out there. I've been just seeing some things about organoids, these little parts of a brain that they grow in a dish and that they can connect up to a computer to build this computer brain interface. So again, these are just some future technologies. You can look at one. So your job then is to pick one of those technologies and look at them. So, and I think I have more listed in the exercise updated list here. So again, in the list, you can look at some of these different ideas here. Choose one of these. And again, what I want you to do is look it up in AI. Tell me what AI model you're using and what AI tells you about it. Find an actual article about it and write a summary of that article. And then tell me your opinion of this. What do you think of one of these? So pick one of these technologies. And if there's something else that's not on the list, you can certainly do that. Something, again, that's some future groundbreaking technology that people are researching. So, okay, so go through this, do this, work through this. Again, if you want to get anything or talk to me about your project, pick up your final project, your Raspberry Pi to work on over break. Talk to me about that. And that'll be our goal for the day. So if you're done with that, you're good. Stop this.